Hey guys, this video took real effort to make. If you want to support that effort and keep this channel alive, consider supporting on Patreon. Link is in the description.
There is something about the feeling of a room going quiet that stays with you. Not the dramatic kind of quiet, not the gasp and stillness that happens when someone drops something. More the other kind, the slow kind, where a conversation just stops because the person in the middle of it has said something and nobody quite knows what to do with it yet. That is more or less what happened in physics in 1928. Paul Dirac was 26. He had this habit, colleagues mentioned it more than once, of working in an almost alarming silence, sitting very still, thinking for long stretches before writing anything down. And what he wrote down, when he finally did, was an equation. One equation. It was an attempt to reconcile two things that had not been reconciled before: the quantum behavior of the electron and Einstein's special relativity. Both were known to be correct. Neither had been made to talk to the other properly. Dirac made them talk. The equation worked. That part was not in dispute. It described the electron beautifully, its spin, its energy, its behavior at speeds approaching the speed of light. Physicists looked at it and saw that it was right. You could feel the rightness of it, apparently. The way certain mathematical structures just settle into place and stop arguing with themselves. But the equation had 4 solutions, not 2. 4. And 2 of those solutions described something that had no business existing. A particle with the same mass as an electron, the same spin, everything the same, but with a positive charge instead of a negative one. The equation was insisting with complete mathematical composure that there was another kind of electron, a mirror electron, one that nobody had ever seen. The chalk dust in those seminar rooms, cold rooms, most of them, the kind where the heating never quite reached the back, must have settled in a particular way when people started talking about what to do with this. What they did, initially, was try to make it go away. Dirac himself spent time suggesting that the positive solutions might correspond to protons. Protons were known, protons were fine. The math didn't really support this. Protons are nearly 2,000 times heavier than electrons, and the equation was describing something with identical mass. But the alternative was worse. The alternative was admitting that the equation was pointing at something nobody had found yet. Something that, by all existing evidence, didn't exist. The alternative was taking the math more seriously than the world. And that is a genuinely uncomfortable position. Not philosophically uncomfortable, I mean physically uncomfortable. The way it feels when someone tells you something true that you weren't prepared to hear. You can't quite stand in the same place you were standing before, but you haven't moved yet either. Dirac eventually moved. In 1931, he published a paper that stopped apologizing for the equation and simply named what it required: an anti-electron, a particle of identical mass and opposite charge. He called it a hole, initially, a gap in a sea of negative energy states, visible precisely because it was absent. The language was awkward. The idea was not. Before we go further, this channel has no sponsors. It runs because some of you choose to make it run, and we still have not reached stable ground yet. Out of 25,000 people, only 200 Patreon members is what this project needs. On Patreon, I share comparison PDFs on things like black holes versus neutron stars, audio biographies of scientists both celebrated and almost entirely forgotten, people like Paul Ehrenfest, whose story I genuinely was not prepared for, search notes for every video on this channel, and deeper audio explorations for topics that go far beyond what a single video can hold. If any of that sounds worth being part of, the link is in the description. The physics community's response was something between skepticism and resignation. Nobody rushed to confirm it. There was no excited scramble to build a detector. Most people, it seems, were quietly hoping the problem would sort itself out, that someone would find an error, or a better interpretation, or some reason to set the positive solutions aside without consequence. The thing about a correct equation is that it doesn't care about any of that. It just keeps being correct. And here is the part that I still find hard to sit with, or maybe, I should say, the part that doesn't quite resolve no matter how many times I think it through. The equation wasn't predicting something exotic. It wasn't predicting something far away or ancient or savely hypothetical. It was predicting that for every particle of ordinary matter, there should exist a counterpart, an opposite, that the electron you are made of right now in this moment has a twin of equal mass and opposite charge written into the same mathematics that describes the electron itself. Not a metaphor, not a convenience, a structural demand. The equation wasn't speculating, it was in its silent mathematical way insisting, and in 1932, 1 year after Dirac named the anti-electron, Carl Anderson, studying cosmic rays in California, found a track in a cloud chamber that curved the wrong way. The equation had been right the whole time, which means the universe had been holding this secret since before anyone thought to ask. What that implies for the universe we actually live in, for how matter came to exist at all, is where the stranger part of this begins. The cloud chamber wasn't a glamorous instrument, a sealed container mostly, supersaturated vapour inside, alcohol-based, with that particular sharp, clean smell that clings to lab coats and doesn't quite leave, and when a charged particle passed through, it left a visible trail, a line of tiny droplets, like breath in cold air, but thinner. More precise, Anderson was 27, working at Caltech studying cosmic rays, which meant he was essentially pointing his detector at the sky and waiting to see what fell through. Most of what fell through was ordinary, electrons mostly. Their trails curved in a known direction under the magnetic field he'd applied, negative charge, predictable bend, nothing to write about. August 2nd, 1932. A particle passed through the chamber and left a track. It curved the wrong way. Not the wrong way by a little, the wrong way completely, opposite to what a negative charge would do in the same magnetic field at the same energy, which meant either the charge was positive or the particle was moving upward through the chamber rather than downward, which Anderson actually considered for a while. He put a lead plate across the middle of the chamber so he could tell which direction particles were travelling. The particle that came next, or one very like it, passed through the lead, slowed down on the other side the way a particle losing energy does, and still curved the wrong way. Positive charge, electron mass. He sat with that for nearly a year before publishing. I find that detail quietly remarkable. Not remarkable in the big pronouncement sense, just it stays with me. A year. He had the photograph, he had the lead plate confirmation, he had the geometry, and he still took a year cross-checking, re-examining, making sure he hadn't done something wrong or missed something obvious. That's not timidity. That's the specific weight of knowing that if you're right, you're holding something that changes the shape of what's real. The paper came out in September 1932. It was careful and measured and used the phrase with due reserve in interpretation, which, given what he was actually saying, is a kind of understatement so extreme it almost becomes its own form of courage. He named the particle a positron for its positive charge. What Anderson probably didn't know, or hadn't fully absorbed yet, was that Dirac's equation had already predicted exactly this. He mentions the connection almost as an afterthought in a later paper, not the announcement. There's something in that. The theorist and the experimentalist arriving at the same doorstep from completely different directions, one through mathematics and one through a photograph of a curving line. A photograph. That's all it was, physically. A glass plate, a pale arc of droplets in a supersaturated vapour. And inside that arc, though nobody quite had the language for it yet, was the first evidence that the universe contains not one kind of matter but two. That for every particle we are made of, something else exists with the same mass and the opposite charge. That the electron in your body has a twin, somewhere, written into the same physics. Blackett and Occhialini confirmed it in 1933. The antiproton came later, 1955, the antineutron the year after that, and eventually in 1995 the first anti-atom, antihydrogen, a positron orbiting an antiproton, assembled for the first time at CERN. All of it traces back to that single curved line. That morning in a California lab when a particle went the wrong way, and a young physicist was careful enough and patient enough to trust what he saw. The question the photograph left open, though, the one it didn't answer. If antimatter exists, if the physics demands it, if the equation requires it, then why, when we look out at the universe in every direction we're capable of looking, do we find almost none of it? that question turns out to be much harder than the photograph. Start with what physics expects, not what it finds, not what we observe when we point instruments at the sky or run particles through accelerators or measure the ancient light still drifting toward us from the first few 100,000 years. Set all of that aside for a moment. Start only with what the equations, taken seriously, on their own terms, actually require. They require balance. Every process in the standard model of particle physics, every interaction, every decay, every collision, obeys a symmetry between matter and antimatter that is, for most purposes, nearly absolute. When energy converts to mass, it converts to both. A photon with enough energy becomes an electron and a positron together, not one without the other. You cannot, through ordinary physical processes, manufacture matter without simultaneously manufacturing its opposite. The bookkeeping is meticulous. The ledger always closes, so if you take that symmetry seriously, if you follow it back to the beginning. The Big Bang was, among other things, an event of extraordinary energy density, conditions so extreme that matter was being created continuously, spontaneously from pure radiation. Quarks, antiquarks, leptons, antileptons, all of them boiling into existence and back out again in a thermal plasma that was, in those first fractions of a second, hotter than anything that has existed since. And if the laws governing that process were symmetric, if matter and antimatter were being produced in equal measure, which is what the physics suggests they should have been, then the early universe contained, in rough equilibrium, equal quantities of both. That is where the calculation starts to feel uncomfortable, because equal quantities of matter and antimatter, in close proximity, in a hot dense plasma, do not coexist indefinitely. They find each other, and when they find each other, they annihilate. Not violently, not explosively in the way we imagine explosions, but completely. Two particles, one matter, one antimatter, meeting and converting entirely to photons. No residue, no ash, just light. In a universe where matter and antimatter were produced in truly equal amounts, that process would have continued until there was nothing left to annihilate. The plasma would have cooled. The pairs would have found each other, one by one, until the last proton met the last antiproton, the last electron met the last positron, and the universe settled into a state of pure radiation, photons expanding outward through an increasingly cold and empty space. No atoms. That part is worth sitting with. Not just no stars, no planets, no chemistry. No atoms. Because atoms require protons, and protons are matter, and in this version of the universe there are none. There is only light, spreading thin across a space with nothing in it to absorb it, nothing to gather it, nothing to warm. The darkness behind closed eyes is not quite black. It's more like the absence of any colour that has a name, and that is, actually, closer to what this universe would be than any darkness we experience here. No surfaces to be dark, no medium for darkness to mean anything. This is what symmetry produces, and symmetry, to be clear, is not an assumption made carelessly. It is not a starting point chosen for convenience. The symmetry between matter and antimatter is written into the structure of quantum field theory at a level so deep that violating it requires specific, deliberate, experimentally confirmed mechanisms. It is the default. It is what you get if nothing intervenes, which means our existence, the atoms, the stars, the accumulated weight of everything that has ever been anything, is evidence that something intervened. Something in the first moments of the universe broke the balance, tipped the ledger, produced somehow slightly more matter than antimatter, not by much, not by anything you would call a large margin, but enough. Enough that when the annihilation finished, when matter and antimatter had found each other and cancelled as completely as physics allowed, there was a remainder, a residue, us. The question of how that happened, what broke the symmetry, what mechanism, what property of matter and antimatter made them not quite equal after all, is one of the genuinely open problems in physics. Not open the way some problems are open, where the answer is suspected and the work is confirmation. Open the way a room is open when you don't know what's in it. Whether destruction is even quite the right word for what would have happened in a symmetric universe, I am not sure. Erasure, maybe. Completion. The universe fulfilling its own symmetry so thoroughly that it left nothing behind to notice. Which is, in its way, the strangest part. The universe we actually have is the one that failed to be symmetric enough. And the size of that failure, 1 part in 10 billion, give or take, is what everything you have ever seen is made of. 1 in 10 billion? Hold that for a second before moving past it. Not as a statistic, not as a physicist's shorthand, just as a ratio. For every 10 billion particles of antimatter produced in the early universe, there were 10 billion and 1 particles of matter. That single extra particle, 1 in 10 billion, is the reason anything exists. Every atom in your body, every star visible on a clear night, every planet, every grain of dust drifting through interstellar space, all of it descended from that surplus, from the remainder left behind after the annihilation finished. 1 in 10 billion. The number has a formal name. Physicists write it as eta, the baryon-to-photon ratio, and its measured value is approximately 6 times 10 to the power of minus 10, which is another way of writing the same thing. Roughly 6 baryons for every 10 billion photons in the universe today. The photons are the record of the annihilation. Every time a matter-antimatter pair found each other and cancelled, they became light. That light is still here. It fills the universe in every direction, cooled now to just a few degrees above absolute zero, detectable as the cosmic microwave background, a faint, cold hum that our instruments can map with extraordinary precision. The baryons, protons, neutrons, eventually atoms, eventually everything, the remainder. So there are 2 ways to weigh this remainder. 2 completely separate methods that physicists developed independently using different physics, different data, different epochs in cosmic history, and both of them land on the same number. The first method comes from the first few minutes. Big Bang nucleosynthesis is the process by which the universe's first light elements were forged as hydrogen, helium, traces of lithium, in the window between about 1 second and roughly 20 minutes after the Big Bang. When temperatures are dropped enough for protons and neutrons to begin binding together without immediately flying apart. The rates of those reactions, the ratios of elements that emerged, depend sensitively on how many baryons were present per photon. Too many baryons, and you get too much helium. Too few, and the proportions shift the other way. The abundances of hydrogen and helium and deuterium that we measure today in the oldest, least processed regions of the universe. Those abundances pin down ETA independently of anything else. The second method comes from much later. 380,000 years after the Big Bang, the universe cooled enough for electrons to bind to nuclei and form neutral atoms. Before that moment, the plasma was opaque. Photons couldn't travel freely. They just scattered endlessly off charged particles. The moment neutral atoms formed, the universe became transparent, and the photons streamed out. That light is the CMB. Its temperature fluctuations, tiny ripples, 1 part in 100,000, encode the physics of the plasma it escaped from, including how many baryons were present. The pattern of peaks and troughs in the CMB power spectrum, measured now with extraordinary care by satellites and ground-based observatories, gives an independent determination of ETA, 2 methods, 380,000 years apart in cosmic time. Different physics entirely, same number. That agreement, I want to call it beautiful, and I keep pulling back from that word because it feels like it softens something that should stay hard-edged. The word I'll use instead is clean. The agreement is clean. A universe in which the early universe nucleosynthesis and the CMB imprint both independently point to ETA approximately 6 times 10 to the power of minus 10 is a universe that is being internally consistent in a way that is not guaranteed. It didn't have to work out that way. The fact that it does is confirmation, quiet and firm, that the picture is basically right. There's a coin weight quality to the number when you sit with it. Not heavy, light, actually. Almost nothing. A ratio so small it barely registers. 6 survivors per 10 billion collisions. Hold that in your palm and you're holding the accounting of everything. What the number doesn't tell you is why. Why was the surplus 1 in 10 billion and not 0? What broke the symmetry? The arithmetic records the outcome with clean precision. The cause, the mechanism, the moment, the physical process that tilted the ledger before the annihilation began. That part the number stays quiet about. It just tells you the surplus existed, and that the surplus was enough. Before there were atoms, there were nuclei. Before there were nuclei, there were protons and neutrons. Before there were protons and neutrons, and this is the part that requires a certain willingness to let go of ordinary intuitions about what matter is and how it behaves. There was something else entirely, a state of matter so hot, so dense, so fundamentally different from anything that exists in the universe today that calling it a plasma is accurate and also, in a quiet way, not quite enough. The word plasma usually brings to mind something thin and glowing, the gas inside a fluorescent tube, the corona of the sun, visible during an eclipse as a pale fringe against the dark. Those plasmas are hot by ordinary standards, tens of thousands of degrees, millions in the corona's case, and they're genuinely strange relative to everyday experience, electrons stripped from their atoms, charged particles moving freely through a conducting medium. The Quark-Gluon Plasma is not that, not remotely. In the first microsecond after the Big Bang, boom, not the first second, not the first millisecond, the first microsecond, the temperature of the universe was somewhere around 2 trillion degrees. To put that in terms of energy, which is how physicists prefer to frame it, roughly 200 mega-electron volts per particle. At those temperatures, the strong nuclear force which ordinarily binds quarks together inside protons and neutrons with a grip so tenacious that it strengthens rather than weakens as quarks try to pull apart simply cannot maintain confinement. The thermal energy of individual quarks exceeds the binding energy that would hold them inside a hadron. They move freely. Freely is perhaps not quite the right word either. They move, but they move through each other, through a medium so dense that every cubic centimetre contained more energy than anything in the present universe outside of black hole interiors, and through that medium they interacted continuously, colliding and exchanging gluons and changing colour charge and converting moment to moment between quark types. Up quarks becoming down quarks, strange quarks flickering in and out of existence, and alongside every quark, an anti-quark, produced in the same thermal processes, annihilating and reforming with a relentlessness that has no analogy in the present-day universe at all. There is a particular quality to heat that has no surface, not warmth radiating from a fire, not the sting of sunlight on skin, but heat that fills a space completely, pressing in from every direction with equal weight so that there is no cooler direction to turn toward. The Quark-Gluon Plasma was that, at a scale and intensity that makes the description feel inadequate even as it is the most accurate one available. And in that plasma, matter and antimatter existed in something very close to equality, very close, not exact. The asymmetry was already there, written into the conditions of the plasma by whatever mechanism had tilted the ledger in the first fraction of a second, before even the quark-gluon phase had fully established itself. But it was invisible in the noise of continuous creation and annihilation. For every quark, an antiquark. For every antiquark, a quark. The exchange was so rapid, the equilibrium so thoroughly maintained by the temperature of the plasma, that the tiny surplus of matter over antimatter, 1 part in 10 billion, was completely submerged. It existed. It just didn't show. Think of it this way, though. No. Actually, the comparison I was reaching for doesn't quite hold. The surplus in this plasma was less like a small imbalance in a large transaction, and more like something written in the substrate of the transaction itself, invisible until the transaction slowed enough to be read. That is closer. Not a ledger entry that stands out, but a property of the ink. The plasma lasted in this quark-gluon state for somewhere between 10 and 40 microseconds, depending on which processes you're tracking and where you mark the transition. Time at this scale is strange to reason about. A microsecond is 1/1,000,000th of a second, and yet within those tens of microseconds the universe was evolving through conditions that will never recur, running through a sequence of thermal states as it expanded and cooled, each state leaving constraints on everything that would follow. At around 155 to 170 mega-electron volts, a temperature the universe reached somewhere between 20 and 40 microseconds in, something shifted. Not abruptly, not as a sharp phase transition in the strict thermodynamics sense, but as a crossover, a gradual thickening, a binding, quarks beginning to find each other and hold. The colour force reasserting itself as the ambient thermal energy dropped below the threshold that had kept confinement at bay. Quarks began to bind into hadrons. Protons and neutrons and a large variety of heavier, unstable particles formed from the cooling plasma and immediately began decaying or colliding or annihilating. The quark-gluon phase was ending. The universe was entering a new regime, denser with hadrons now, matter and antimatter still present in an enormous quantities, still finding each other, still converting back to radiation, but structured differently than before. The substrate had changed, and somewhere in that structure, the asymmetry waited. Patient is the wrong word. It had no properties, no intentions, no awareness of what it was. It was just a number, a ratio, 1 in 10 billion. It would matter very soon. The transition was not an event, exactly. There was no threshold crossed in an instant, no single moment when the quark-gluon plasma ended and the next phase of the universe began. It was a cooling, gradual, inevitable, governed entirely by the expansion of space pulling energy outward and thinning the temperature of everything inside it. And as the temperature dropped through that critical range around 155 to 170 mega-electron volts, the strong nuclear force began to reassert what thermal chaos had been suppressing. Quarks found each other, bound, became protons, neutrons, pions, kaons, a whole catalogue of hadrons both stable and deeply unstable. The unstable ones decaying almost immediately into lighter particles, the stable ones persisting and moving through the plasma and finding, with growing frequency as the density of the medium shifted, their antimatter counterparts. A proton meeting an antiproton, a neutron meeting an antineutron, the meeting lasting an almost immeasurably short time before both particles ceased to exist as particles at all and became instead photons. High-energy gamma rays mostly, pure radiation carrying the combined rest mass energy of both particles away at the speed of light. This is the point where the word annihilation gets used so routinely in physics discussions that it starts to feel like a technical term, neutral, descriptive, carrying no particular weight. It's worth stopping that habit for a moment. Annihilation is the complete conversion of matter into radiation, not a chemical reaction, not a nuclear reaction in the ordinary sense, but the total erasure of two particles, both of them, leaving nothing behind in the particle sense at all. Two things become no things, the mass becomes energy, the energy disperses. That process, multiplied across a volume of space that was by this point 20 to 30 microseconds after the Big Bang, the size of what would eventually become the observable universe, and proceeding at a rate governed by the density of the plasma and the thermal velocities of the particles moving through it, was the dominant physical process in the universe for the next fraction of a second. When the hadronization completed, or when the quark-gluon plasma had fully transitioned to a hadronic gas of protons, neutrons, and their antimatter equivalents, baryons and antibaryons together constituted roughly 10% of the total energy content of the universe. 10% is not a small number in this context. It means the universe was still, at that moment substantially material, dense with particles, dense with their opposites, that 10% began to fall, not quickly in the way a dropped object falls, but steadily as particle met antiparticle and the meeting consumed both. The density of the medium was still high enough that collisions were frequent. Matter and antimatter were not yet sparse enough to simply miss each other. They found each other, and each finding reduced the total count, and the reduction itself, by thinning the plasma, made subsequent collisions slightly less frequent, and the process had this quality of a tide going out, not retreating in a rush, but withdrawing in a slow and absolute way that left the shore changed. For those of you who prefer reading to listening, most of what this channel explores has a written companion on the Sleepy Physicist's official website. Long form, unhurried, closer to an essay than a transcript. If that's a space you'd want, it's there. By the time the universe was approximately 1 millisecond old, the fraction of energy carried by baryons and antibaryons had dropped dramatically. By 1/10 of a second, it had fallen further. The annihilation was not slowing because it had completed. It was slowing because the universe was expanding and cooling fast enough now that the particles were becoming harder to find, the plasma thinning as space stretched, the mean free path between particles growing longer, collisions growing less frequent. By 1 second after the Big Bang, the fraction of energy in baryons and antibaryons had collapsed from that initial 10% to something in the range of 1 part in 10 million, 100 million times smaller. The plasma had gone from being substantially material to being, in terms of its particle content, almost entirely radiation, with the barest residue of matter remaining. There is a quality to a room after something large has been taken out of it, not immediately obvious, but present in the slight echo of your footsteps, the way sound behaves differently in more open space, the faint sense of negative volume where something used to be. The universe at 1 second had something of that quality. What had been a dense, hot, matter-rich plasma was now thin light, expanding, cooling, and inside that light, almost too sparse to measure, the survivors. Most of them were photons. Billions of photons for every surviving baryon. The photons were not nothing. They carried the universe's energy budget forward. They governed its expansion rate. They would eventually cool into the microwave background we map today. But they were, in a structural sense, the residue of destruction, each one the converted mass of a particle that no longer existed. The baryons that remained were the asymmetry made visible. Not the asymmetry as an abstract ratio anymore, but as actual protons and neutrons, sparse in the cooling radiation. The only matter left because there had been slightly more matter than antimatter to begin with, 1 in 10 billion. The antimatter had found its match and cancelled. The matter had found its match and cancelled. And then the matching stopped because one side ran out first. What was left was not much. In any sense of the word, not much. But it was enough to be, eventually, everything. Nothing ended cleanly. That is worth saying first before anything else. The annihilation did not stop the way a fire stops when you pour water on it, decisively, completely, with a clear before and after. It slowed. It tapered. Matter and antimatter were still finding each other at 1 second after the Big Bang, still annihilating, still converting mass to light, but less frequently than before and less frequently than a moment before that, because the universe was expanding and the plasma was thinning and the distance between any given baryon and any given antibaryon was growing in a way that made collision increasingly unlikely without making it impossible. Freeze out is the word physicists use for this. It's a reasonable word, though it implies cold in a way that slightly misses the point. At 1 second after the Big Bang, the temperature was still around 10 billion degrees. What froze was not the temperature. What froze was the rate of interaction. More precisely, the rate at which matter and antimatter were colliding dropped below the expansion rate of the universe. And once that happened, the remaining particles could no longer find each other fast enough to maintain equilibrium. The process that had been consuming them simply ran out of opportunity. not opportunity in any deliberate sense. There was no searching. Particles do not search. They move through a medium according to their energy and the density of that medium, and when the medium thins enough, the probability of collision in any given unit of time falls below the threshold where annihilation can continue at a meaningful rate. And so the survivors survived, not because they were protected, not because something intervened on their behalf, because the universe expanded past them while they happened to not be colliding. There is a quality to a conversation that has just ended, not the dramatic kind of ending, not an argument, just a normal conversation between two people that reaches its natural close and leaves a silence that hasn't quite settled into background noise yet. And that quality is what the universe had, in some abstract structural sense, at around 1 second. The exchange had been continuous, and then it wasn't, and the particles still present were present in the kind of stillness that follows a long consuming process. The antimatter was gone. Not entirely. There are subtle and important caveats to that, traces and production mechanisms that persist, but for practical purposes, in terms of the primordial supply, it had found its match. It had met the matter it was paired with and cancelled, and the cancellation had been as thorough as physics allowed. What remained was the surplus, the 1 in 10 billion. Protons and neutrons, sparse in a vast and still hot radiation field, no longer threatened by the annihilation that had consumed everything around them, because the thing that would have consumed them was gone, and the photons, enormous numbers of photons carrying the energy of everything that had annihilated, each one the converted mass of particles that no longer existed in particle form. Each one in a sense that is physically accurate, even if it sounds slightly strange. A record. Not a record anyone can read directly, not information in the way that word usually means, but a physical consequence. A causal descendant of an annihilation event in the first second of the universe. Those photons are still here. They have been travelling and cooling and redshifting for nearly 14 billion years, and today they fill the sky in every direction at a temperature of approximately 2.7 degrees above absolute zero, the cosmic microwave background. When we map that radiation, when we measure its temperature fluctuations to 1 part in 100,000, we are looking at the cooled and stretched descendants of the photons produced in the annihilation. The CMB is, among other things, a fossil of the freeze-out, a record of what was lost. Every photon in that ancient bath of light was made from something. A proton and an antiproton finding each other in the first second, a neutron and an antineutron, an electron and a positron. 2 particles becoming 1 photon, or 2, depending on the process, and that photon travelling outward through an expanding universe for billions of years, until it arrives at an instrument we built to receive it. Whether that makes the CMB a kind of memorial is not a scientific question. It is just a thought that arrives sometimes when you look at the maps, those smooth, slightly mottled images of the oldest light we can see, and remember what made it. The surviving baryons, meanwhile, were about to enter a very different phase. Not safety exactly. The universe still had processes that could affect them. Nucleosynthesis would begin within minutes, would build the first nuclei, and the photons were still energetic enough for a while to break them apart as fast as they formed. The next few minutes were their own kind of complicated, but the annihilation was over. The accounting was closed. What survived, survived. In 1967, Andrei Sakharov was 45 years old, living in Moscow, and already under the kind of surveillance that meant his mail was opened, and his conversations were noted, and certain topics were safer left unwritten. He had spent years at the center of the Soviet nuclear weapons program, the hydrogen bomb specifically, and was beginning the slow, costly process of becoming a public critic of the state that had employed him. His security clearance was intact. His reputation inside the Soviet scientific establishment was still enormous, but the distance between what he was permitted to say and what he actually thought had been widening for years. That year, he published a paper, 3 pages, in a Soviet physics journal called JETP Letters. The paper was titled, in translation, Violation of CP Invariance, C Asymmetry and Baryon Asymmetry of the Universe. It did not make headlines. It was not immediately recognized as the thing it turned out to be. It was a short, careful argument about why the universe contains more matter than antimatter, a question that in 1967 was not yet framed as one of the central unsolved problems in physics. The paper identified 3 conditions. Any physical process that could generate a matter-antimatter asymmetry from a symmetric beginning must satisfy all 3 of them, not 2, not one with the others approximately implied. All 3 simultaneously in the same physical system during the same cosmological epoch. Sakharov wrote them down with the particular plainness of someone who has thought carefully and arrived somewhere definite. The first, baryon number must not be conserved. This sounds technical, but the logic is stark. If every physical process conserves the total count of baryons minus antibaryons, then a universe that begins with equal numbers of both will always have equal numbers of both. You cannot generate an asymmetry without a process that changes the net baryon count. There must exist, somewhere in the physics, an interaction that can create baryons without simultaneously creating antibaryons, or destroy antibaryons without destroying baryons, or some equivalent violation of what had, until fairly recently, been assumed to be an absolute conservation law. The second, the laws of physics must distinguish between matter and antimatter. Technically, this means C symmetry and CP symmetry must both be violated, C being the symmetry that relates a particle to its antiparticle, CP being the combined symmetry of charge conjugation and spatial reflection. If the laws are perfectly symmetric, then every process that favours matter has an equally probable mirror process that favours antimatter, and the net result is 0. Something in the physics has to genuinely prefer one over the other, even slightly. The third, the universe must have passed through a period of thermal disequilibrium. In perfect thermal equilibrium, forward and reverse reactions proceed at the same rate. The system is, by definition, not accumulating anything in either direction. An asymmetry cannot build and hold if every process generating it is immediately reversed by its thermodynamic opposite. There must be a departure from equilibrium, a window in which the forward process ran ahead of the reverse long enough to leave a residue. 3 conditions. It does sound almost too tidy. I thought that the first time I encountered them, this feeling that anything reducible to a clean list of 3 must be either incomplete or retrospectively constructed to seem neater than it was. But Sakharov wasn't constructing a framework for elegance. He was identifying necessary conditions, which is a different thing. Not a model of how the asymmetry happened, but a proof of what any model must include. The tidiness, if it is tidiness, belongs to the logic rather than the physics. What makes the paper striking, and this is harder to convey than the conditions themselves, is the context. Baryon number was widely believed in 1967 to be a conserved quantity. CP violation had been discovered experimentally only 3 years earlier in 1964 in the decay of neutral kaons, and its implications were still being absorbed. The idea that these 2 recently troubled symmetries might together, under the right cosmological conditions, generate the matter excess responsible for the existence of everything, that was not a small intuitive leap. It was the kind of connection that requires holding several uncertain things in mind at once and being willing to follow them. The paper Sakharov wrote has that quality old papers sometimes acquire, not from age exactly, but from handling. The corners of an idea softened by many people reading it, returning to it, building from it. It no longer lies flat against the period that produced it. It has escaped its context and become something more durable. And the political atmosphere around its writing, the opened letters, the monitored conversations, the careful calibration of what could be said and where, that was simply the condition of the room in which Sakharov worked. A cold room, in the structural sense. He worked in it anyway. Whether the universe actually satisfies all 3 of his conditions, which mechanisms are responsible, at what energy scale, through what specific physical process, remains more than 50 years later an open question. The conditions are established. The mechanism is not. Sakharov gave physics a set of rules to aim at. The aiming is still underway. Start with what the standard model is, briefly, because it matters for what comes next. It is the most precisely tested physical theory ever constructed. Not the most intuitive, not the easiest to hold in mind, but the most tested. Its predictions checked against experiment after experiment across decades, across energy scales ranging from the very low to the very high, across particle types and interaction modes and decay channels that number in the hundreds. Where it makes a prediction, that prediction is almost always correct. The anomalous magnetic moment of the electron, calculated from the standard model and measured experimentally, agrees to 10 significant figures. That is not a rounding. That is 10 digits of agreement between theory and measurement. So when the standard model turns to the question of the matter-antimatter asymmetry, when you ask it directly, does your physics contain the ingredients to explain why the universe has more matter than antimatter? The initial answer is yes, and the yes is technically accurate. Barrier number violation exists within the standard model, mediated by the Sphaleron processes that become active at high temperatures. CP violation exists within the standard model, encoded in the mixing of quark flavors through a mathematical object called the CMB matrix, the Kabibbo-Kobayashi-Maskawa matrix, which contains a complex phase, and that phase is the source of a genuine, experimentally confirmed asymmetry between matter and antimatter. Departure from thermal equilibrium exists in principle, because the early universe passed through phase transitions. All three of Sakharov's conditions checked against the list. Present, present, present. The paper closes. The last paragraph has been reached, and the answer isn't there, because present and sufficient are not the same thing. The CP violation in the CKM matrix is real. It has been measured in kaon decays, in B meson decays, confirmed multiple times by multiple experiments over decades. It is not a theoretical artifact, it is a physical fact, written into the weak interactions of quarks. But its magnitude is the problem. To generate the observed baryon asymmetry, that ratio of roughly 6 baryons per 10 billion photons, you need a certain minimum amount of CP violation operating through baryon number violating processes under out-of-equilibrium conditions. The standard model's CP violation, when you calculate how much asymmetry it actually produces given the conditions of the early universe, falls short of that minimum by a factor of approximately 10 to the power of 19. 10 to the 19, that is 1 followed by 19 zeros. That is, a numerical comparison start to lose their grip here, which is itself informative about the size of the gap, that is roughly the number of seconds in 300 million years compared to 1. The shortfall is not a rounding error. It is not a matter of uncertain parameters that might be revised upward with better data. 19 orders of magnitude is a gap so large that it means the standard model CP violation is not a slightly insufficient answer to the question. It is, for practical purposes, not an answer at all. The other failure is quieter but equally structural. The electroweak phase transition, the moment in the early universe when the Higgs field acquired its non-zero value and the electroweak symmetry broke, needed for electroweak baryogenesis to work to be a strongly first-order phase transition. A sharp, discontinuous change, the kind that involves bubble nucleation and expanding interfaces and regions of space in different thermodynamic phases simultaneously. That sharpness is what provides the departure from thermal equilibrium that Sakharov's third condition requires. With a Higgs boson mass of approximately 125 Geiger electron volts, which is what we measured at the LHC in 2012, and the measurement is not uncertain. The electroweak phase transition is not first order. It is a smooth crossover, a gradual continuous shift rather than a sharp transition. The kind of change that doesn't produce the violent out-of-equilibrium dynamics that baryogenesis needs. It is, in the blunt language of thermodynamics, insufficient. So the standard model contains CP violation that is 19 orders of magnitude too small and a phase transition that is the wrong kind. Both problems together, not one saving the other. This is what I mean by confession, though it is not quite the right word, and I'm not sure there is a right word for it. The standard model does not confess in any active sense. It simply is what it is, and what it is happens to be a theory that can name all three of the conditions required to explain our existence, without being able to satisfy any of them quantitatively. It points at the answer, it has the right vocabulary, it describes the shape of the solution clearly enough that you can use it as a guide to look elsewhere. But when you ask it to actually produce the asymmetry, to run the numbers, to show its work, the result is a very particular kind of quiet inadequacy. Not wrong, not broken, just not enough. Which means the physics that actually generated the matter excess, the mechanism that tilted the ledger in the first fraction of a second, lies outside of the standard model. In what direction, through what process, at what energy scale? These are open questions. The standard model can tell you what the answer must do. It cannot tell you what the answer is. That distinction is where the interesting physics begins. Begin with something than a Sphaleron, because the Sphaleron requires a certain amount of groundwork before it becomes approachable. Imagine a landscape, not a dramatic one. No cliffs, no peaks dissolving into cloud. Something more ordinary, a series of valleys, people separated by hills, extending in both directions as far as the landscape goes. Each valley is a low point. Each hill is a high point. If you place an object in one of the valleys, it stays there. It is at a local minimum of energy, and without a push large enough to carry it up and over the hill, it remains. The valleys are stable, the hilltops are not. Now imagine that the valleys are not just geometrically distinct, but topologically distinct. Not merely in different locations, but different in a way that cannot be undone by any continuous deformation. The way a sphere is topologically different from a torus, because you cannot smoothly reshape one into the other without cutting. Each valley in this landscape belongs to a different topological class. Moving from one valley to the next doesn't just change your position, it changes something about the fundamental structure of where you are. This is, roughly, the situation of the electroweak gauge field. The vacuum states of the electroweak field, the lowest energy configurations it can occupy, are not all the same. They form a sequence of distinct topological classes, labelled by an integer called the Chern-Simons number, and the transitions between them are not continuous deformations. They are topological jumps. Moving from one vacuum to the next changes the Chern-Simons number by 1, and each such change, each crossing of the barrier between topologically distinct vacua, changes the baryon number of the universe by 3. 3 baryons created, or 3 baryons destroyed per vacuum transition, not approximately 3, exactly 3, because the topology is exact. The Sphaleron is the field configuration that sits at the top of the barrier between vacua, the hilltop in the landscape analogy. A Sphaleron is not a particle. That distinction is worth holding carefully, because the language of particle physics makes it tempting to imagine a small discrete object, something localized and countable. The Sphaleron is a configuration, which is an honest word, if a strange one for something capable of changing the baryon number of the universe. It is an extended arrangement of fields spread across a region of space with a characteristic size, roughly 10 to the power of minus 16 meters, that represents the maximum energy point on the path between two topologically distinct vacua. The energy of that maximum is approximately 8 to 10 TeV. That number matters enormously for what the Sphaleron does and doesn't do at different temperatures. There is a particular quality to standing at the top of something unstable, not the dizziness of height exactly, but the specific knowledge that the position you occupy requires no additional push to leave, that the slightest perturbation in any direction begins a descent. The Sphaleron has that quality. It is an unstable saddle point. It does not sit at the top of the barrier and persist. It sits there only in the sense that the configuration exists as a mathematical solution. In practice, any field system that finds itself near a Sphaleron configuration will immediately roll off it, transitioning into one of the adjacent vacua, changing the baryon number by 3 in the process. At low temperatures, the temperatures of the universe today, the temperatures of any environment we can create or observe, this transition is suppressed exponentially. To cross the barrier thermally requires a fluctuation of 8 to 10 TeV concentrated in a region of 10 to the power of minus 16 meters. The probability of this happening spontaneously at room temperature is not zero in the technical sense. It is, however, so close to zero that it will not happen within the observable lifetime of the universe. Baryon number, for all practical purposes, is conserved today. The Sphaleron is inert. At high temperatures, the temperatures of the early universe, specifically around and above the electroweak scale of roughly 100 giga-electron-volts, the situation is entirely different. Thermal fluctuations at those temperatures are energetic enough to drive the field over the barrier without tunneling. The Sphaleron transitions are not suppressed. They happen rapidly, continuously, at a rate proportional to the temperature to the 4th power. The electroweak vacuum is not sitting quietly in a single valley. It is sloshing back and forth between adjacent topological states, crossing the barriers repeatedly, and each crossing is changing the baryon number of the universe. What this means for baryogenesis is that Sphalerons, in the early universe, were not a curiosity. They were a central mechanism. They were the process by which baryon number could be both violated and generated, the physical pathway through which a lepton asymmetry could be converted into a baryon asymmetry, the engine, if that word doesn't carry too much mechanical connotation, that could run the ledger in either direction depending on what other conditions were present. Nobody has ever observed a Sphaleron transition directly. The energy required to approach one deliberately in a collider is beyond anything currently achievable, and the probability of one occurring spontaneously at accessible temperatures is negligible. They exist, for now, as mathematical objects whose consequences we can calculate and whose role in the early universe we can infer, but which have never been seen. That gap between theoretical certainty and observational absence is not unusual in cosmology. Much of what happened in the first second of the universe is known through inference rather than observation. The Sphaleron is one entry in a longer list of things we are confident about, without having watched them happen. The confidence comes from the mathematics, and the mathematics, in this case, is consistent and clear. The topology is real, the barrier is real, the baryon number change per crossing is exact. Whether the transitions happened in the right direction, at the right rate, under the right conditions, to produce the asymmetry we observe, that depends on what else was present in the early universe alongside the Sphalerons. Which is where the next layer of the problem begins. Picture the universe at roughly 100 billionths of a second after the Big Bang, not the very beginning, not the Quark-Gluon Plasma era, but a slightly later moment when the temperature has dropped to around 100 giga-electron-volts, and the electroweak force is about to do something it has only ever done once. The Higgs field at this temperature has not yet settled. It exists throughout space in a symmetric state, a kind of undifferentiated potential, present everywhere but not yet committed to a non-zero value in any particular direction in field space. The electroweak symmetry is unbroken. The W and Z bosons are massless. The quarks and leptons are massless. The universe is a plasma of massless or nearly massless particles interacting at high rates in a hot, dense medium, and Sphalerons are crossing the topological barriers between electroweak vacua rapidly and continuously, changing baryon number at a ferocious rate in both directions equally. Then the transition begins. Bubble is not quite the right word for what forms, but it is the word that exists, so it will have to do. In a first-order phase transition, which is what electroweak baryogenesis requires, and which the standard model with a 125 electron-volt Higgs does not provide, but which certain extensions of the standard model do. The Higgs field does not shift uniformly across all of space simultaneously. Instead, small regions nucleate, pockets where the Higgs field has tunneled or fluctuated into the broken symmetry phase, where it has acquired a non-zero vacuum expectation value, and the electroweak symmetry is locally broken. These pockets are surrounded by the still symmetric plasma. They expand. Their walls, the boundaries between broken and unbroken phases, move outward through the plasma at a significant fraction of the speed of light. There is a particular sensation to approaching a boundary you cannot see. A pressure change, a slight temperature differential, something in the quality of the air that tells you a threshold is near before you have any visual evidence of it. The bubble wall in this scenario has something of that quality if you try to locate yourself as a particle in the surrounding plasma. On one side, the symmetric phase, the Higgs field unbroken, sphalerons active, baryon number changing. On the other side, the broken phase, the Higgs field settled, Sphaleron activity exponentially suppressed, baryon number frozen. The wall is where the physics happens. As the bubble wall moves through the plasma, particles in the symmetric phase interact with the changing Higgs field at the boundary. These interactions are CP violating. The Higgs field profile across the wall creates conditions where quarks and their antimatter counterparts behave differently, scattering off the wall at different rates, penetrating to different depths, reflecting with different probabilities. The CP violation generates a slight excess of left-handed quarks over left-handed antiquarks in the symmetric phase just ahead of the wall. This is a small effect, a fractional difference in scattering rates, producing a small chiral asymmetry in the plasma immediately outside the bubble. The sphalerons see this asymmetry. Sphaleron transitions, which have been running continuously in both directions, are sensitive to the local density of left-handed fermions. The slight excess generated by CP violating scattering at the wall biases the Sphaleron transitions toward producing baryons rather than antibaryons. The Sphaleron is not choosing, there is no mechanism of choice, but the CP asymmetric environment tips the statistical balance. Slightly more baryon number increasing transitions than decreasing ones. A net production of baryons in the symmetric phase just ahead of the expanding wall. Those baryons are then swept up by the advancing wall. They cross into the broken phase, where Sphaleron activity is suppressed, where the baryon asymmetry cannot be washed out or reversed. The asymmetry is frozen into the broken symmetry region as the wall passes. Each parcel of the universe that the bubble wall sweeps through contributes a small excess of baryons, locked in as the wall moves on. The process continues until the bubbles fill the universe completely, until the entire cosmos has transitioned to the broken phase and the electroweak symmetry breaking is complete. What remains is the accumulated baryon excess generated at the walls of all those expanding bubbles, frozen into the now stable broken symmetry vacuum. This mechanism has a quality that most baryogenesis proposals lack. It is testable. The CP violation required to drive it must be large enough to generate the observed asymmetry, which means it must be large enough to leave signals at the LHC, in the Higgs sector, in the properties of the W boson, in processes involving the top quark. The requirement for a strongly first-order phase transition also implies modifications to the Higgs potential that collider experiments can constrain. Electroweak baryogenesis makes predictions at energies we can actually reach with existing technology, which is, this is not a small thing, genuinely unusual for a baryogenesis mechanism, and yet. The LHC has been running for 15 years. The Higgs boson mass is 125 gigaelectronvolts, which, as discussed before, means the standard model electroweak phase transition is not first order. Extensions of the standard model that could make it first order, additional scalar fields, modifications to the Higgs potential, are increasingly constrained by experiment. The additional CP violation required has not appeared in any measurement. The new physics that electroweak baryogenesis needs has been searched for, carefully and extensively, and has not been found. This does not rule it out. Absence of evidence in a finite dataset is not evidence of absence, and the LHC's successor experiments will probe deeper. But the comfortable version of the mechanism, the one that required only modest extensions of known physics at the electroweak scale, is under considerable pressure. The parameter space in which it works is narrowing. What remains is a mechanism that is coherent, physically well motivated, connected to testable predictions, and probably not the complete explanation for why we exist, which is its own kind of position to occupy. Not wrong, not ruled out, but insufficient, sitting in the same region of physics as the Standard Model's own CP violation, capable of pointing towards the answer without quite being it. The universe, it seems, required something more. Go back further than the electroweak phase transition, past the 100 GeV scale where the Higgs field settled and the Sphaleron transitions froze, past the temperatures that electroweak baryogenesis required. Go back to a period so early in the universe's history, so energetic, so dense, so far from anything a particle accelerator has ever approached, that the physics operating there is, for now, accessible only through inference and mathematical consistency rather than direct observation. At energies somewhere between 1 billion and 10 million billion GeV, the range is genuinely uncertain. The theory does not pin it down precisely. The universe may have contained a class of particles that do not exist in the present-day cosmos and have never been produced in any laboratory on Earth. They are called right-handed neutrinos, though the name is somewhat misleading in the way that many names in particle physics are misleading. The handedness refers to a property called chirality, a quantum mechanical quantity related to the relationship between a particle's spin and its direction of motion. Right-handed here is a technical designation, not a spatial one. It has nothing to do with hands. What matters about these particles is not their handedness, but their mass and their behaviour. The right-handed neutrinos of leptogenesis are heavy, very heavy, possibly as heavy as 10 to the 9, or 10 to the 13, or 10 to the 16 giga-electron volts, depending on which version of the theory you're working with. For comparison, the proton mass is approximately 1 giga-electron volt. These are particles whose masses sit at scales anywhere from 1 billion to 10,000 trillion times heavier than a proton. They are so massive that the thermal energy of the early universe, which is in rough equilibrium with the temperature of the plasma, can produce them only at extremely early times, and once the universe cools below their mass scale, they can no longer be produced, they decay. The decay is the event that matters. A right-handed Majorana neutrino can decay into a lepton and a Higgs boson, or into an antilepton and an anti-Higgs boson. In a perfectly CP-symmetric world, it would decay into both channels with equal probability, and the net lepton number produced would be 0. But CP symmetry, as established by the Sakharov conditions, must be violated. The right-handed neutrino decays into leptons slightly more often than it decays into antileptons. The asymmetry is small, a few parts per million depending on the parameters, but it is non-zero, and it accumulates across an enormous number of decays occurring out of thermal equilibrium in the early plasma. Out of equilibrium is the critical phrase. If the decay were happening in perfect thermal equilibrium, the reverse process, lepton and Higgs boson, combining to recreate a right-handed neutrino, would proceed at exactly the same rate, washing out any asymmetry as fast as it formed. But the universe is expanding. The expansion rate at the temperatures relevant to leptogenesis is fast enough that the heavy neutrinos fall out of equilibrium before they finish decaying. The reaction rate drops below the Hubble rate, and the reverse process can no longer keep up. The asymmetry is not erased. It builds. What accumulates is a slight excess of leptons over antileptons, not baryons, leptons, electrons, muons, tau particles, their associated neutrinos. The matter-antimatter asymmetry at this stage lives in the lepton sector, and then the sphalerons take over. The Sphaleron processes, active at high temperatures in the symmetric phase of the electroweak era, do not distinguish between baryon number and lepton number in the way conservation laws at low temperatures do. They violate both B and L, baryon number and lepton number, while conserving the combination B minus L. This means that a lepton asymmetry in the presence of active sphalerons is not stable. The sphalerons redistribute the asymmetry between the lepton and baryon sectors, partially converting the lepton excess into a baryon excess, until the combination reaches a new equilibrium consistent with the B-L conservation. The fraction that ends up as baryons is determined by the electroweak physics and works out to approximately a third of the original B-L asymmetry. The lepton asymmetry becomes a baryon asymmetry. The baryons survive into the present universe as protons and neutrons, as atoms, as everything. Now consider the ordinary neutrinos, the 3 light neutrinos we have measured, whose masses are known to be tiny, less than 1/10 of an electron volt each, which makes them somewhere between 500,000 and 5 billion times lighter than the electron, depending on which neutrino you're comparing. They are extraordinarily light. No other known fermion is remotely as light relative to the electroweak scale. There is a thin wire under tension quality as the seesaw mechanism, the way something slight and almost invisible turns out to be holding an enormous weight. The seesaw works like this. If a right-handed neutrino exists with a very large Majorana mass m, and if it couples to the ordinary left-handed neutrino through a Yukawa interaction with coupling strength similar to other particles, then the mass of the ordinary light neutrino is suppressed by a factor of roughly the electroweak scale squared divided by m. The heavier the right-handed neutrino, the lighter the left-handed neutrino. The two masses sit at opposite ends of a lever. Push one end very high and the other end is pushed very low. This is why the light neutrino masses are so small. Not because neutrinos are special in some unmotivated way, but because their right-handed counterparts may be extraordinarily heavy, at exactly the scales relevant to leptogenesis. The same right-handed neutrinos that generate the lepton asymmetry that eventually becomes the baryon asymmetry that produced all the matter in the universe are also responsible, through the seesaw, for the extraordinary lightness of the neutrinos you are made of. One mechanism, 2 consequences, the matter excess and the neutrino mass spectrum, both following from the same particles at the same energy scale through related but distinct physical processes. Whether this is a genuine double explanation or a remarkable numerical coincidence is, honestly, not something I can resolve. The theory is consistent. The two phenomena connect. Whether nature actually chose this path, whether right-handed neutrinos at these scales truly existed in the early universe, is a question that may not be answerable with any instrument currently planned or conceived. The energy scales involved are simply too high. Leptogenesis operates at temperatures the universe reached in its first tiny fraction of a second, at energies that no collider on Earth approaches, and none that could be built on Earth within any planning horizon we can articulate would approach. The mechanism is mathematically coherent, physically well motivated, and almost entirely beyond direct experimental verification. That tension, between explanatory reach and experimental inaccessibility, is something leptogenesis carries quietly. It does not announce it. The mechanism simply is what it is, and what it cannot be is tested in the ordinary sense. What it can be is constrained, and the constraints increasingly come from neutrinos themselves. Neutrinos change. Not in the way particles usually change, not by decaying into something else, not by interacting with a field and acquiring new properties. They change by travelling. A neutrino produced as one flavour, electron, muon or tau, named for the charged lepton it is associated with, will, as it moves through space, oscillate between those flavours with probabilities that depend on how far it has travelled, how much energy it carries, and the values of several mixing parameters that describe how the 3 neutrino mass states relate to the 3 flavour states. This is neutrino oscillation, and it is experimentally confirmed beyond any reasonable doubt. It was confirmed well enough to earn a Nobel Prize in 2015. What it implies, that neutrinos have mass because massless particles cannot oscillate, was itself a modification to the Standard Model, which had originally predicted massless neutrinos. The masses are tiny, but they are not zero. What the oscillation experiments have been trying to measure, in the years since, is not just that oscillations happens, but the precise parameters governing it. The mixing angles, 3 of them Boeds, describe the rotation between mass and flavor eigenstates. The mass-squared differences, 2 independent ones, describe how far apart the 3 mass states are from each other, and one parameter, a phase angle called delta Cp, describes whether the oscillation behaves differently for neutrinos than for antineutrinos. That last parameter is the one that connects to Cp violation, and Cp violation in the lepton sector is what connects through the leptogenesis mechanism to the matter-antimatter asymmetry of the universe. T2K and NOVA are both long baseline neutrino oscillation experiments. T2K fires a beam of muon neutrinos from the J-Park accelerator on the east coast of Japan across 295 kilometers to the Super Kamiokande detector. NOVA sends a beam from Fermilab in Illinois to a detector in Ash River, Minnesota, across 800 to 10 kilometers. Both measure how many of the muon neutrinos have oscillated into electron neutrinos by the time they arrive, and both do this separately for neutrinos and antineutrinos. The difference in oscillation probability between the two is the Cp violating signal they are looking for. They are nominally rivals. The same measurement, roughly, pursued by different collaborations on different continents with different baselines and different systematic uncertainties. There is something slightly unusual about 2 such experiments producing a joint paper, the kind of thing that requires a certain institutional willingness to set aside the ordinary competitive structure of experimental physics. The paper came out in October 2025, published in Nature, and you read a result like that a few times before you accept what it's actually saying. Not from disbelief, just from wanting to be sure. What the joint analysis found, the uncertainty in the neutrino mass squared differences reduced to below 2%, a meaningful improvement in precision that comes from combining datasets with different sensitivity profiles. And on the question of Cp violation, on the value of delta Cp, the combined result found something that depends critically on which way the neutrino masses are ordered. There are 2 possibilities for the neutrino mass ordering. In the normal ordering, the lightest of the 3 mass states is the one most closely associated with the electron neutrinos, and the heaviest is the one most closely associated with tau neutrinos. In the inverted ordering, the relationship is reversed. The heaviest 2 states are close together, and the lightest is separated below them. The 2 orderings lead to different predictions for oscillation probabilities at different baselines and energies, which is why 2 experiments with different baselines, 295 kilometers and 810 kilometers, provide complementary information. The combined NOVA and T2K analysis does not yet determine the mass ordering definitively. Both orderings remain consistent with the data, but here is the part that requires sitting with carefully. If the mass ordering is inverted, the combined result provides evidence for Cp violation in the lepton sector. Not proof, evidence. A hint with a specific quantitative shape pointing in a specific direction, consistent with a value of delta Cp that would produce more electron neutrinos than electron antineutrinos in a long baseline beam. Which is Cp violation. Matter and antimatter behaving differently in the lepton sector at energies accessible to existing detectors. The connection to leptogenesis is real but indirect. The Cp violation that drives leptogenesis happens at energy scales, many orders of magnitude above what any oscillation experiment can probe. The heavy right-handed neutrinos that generate the lepton asymmetry are far too massive to be produced or observed directly. Measuring delta Cp in neutrino oscillations does not measure the Cp violation parameter in leptogenesis directly. They are related, but the relationship depends on the specific model of leptogenesis being considered, and different models predict different connections. What a non-zero delta Cp would establish is that Cp violation exists in the lepton sector at all, that the lepton sector is not Cp symmetric, that neutrinos and antineutrinos behave differently in a measurable way. This would not confirm leptogenesis, but it would make it considerably harder to argue against. It would show that the lepton sector has exactly the kind of asymmetry that leptogenesis requires, Even if the specific numbers don't directly translate, the data is suggestive. It is not conclusive. The mass ordering is unknown. The significance of the CP violation hint in the inverted ordering scenario is not yet at the threshold physicists conventionally require for a discovery claim. More data is coming from extended T2K and NOVA runs, from the next-generation experiment Hyper Kamiokande beginning operations in Japan, from Dune being constructed in the United States. There is a particular quality to holding a result that might be the answer. Not the answer written out clearly, more like the answer's outline, visible through something slightly opaque, clear enough that you can see there is a shape there, not clear enough to read what the shape says. That is roughly where neutrino physics sits right now. The shape is there. The reading is still coming. Every mechanism discussed so far has lived at a transition, at the electroweak phase transition, at the decay of heavy neutrinos, at the bubble walls of a changing vacuum. They are all, in different ways, stories about boundaries, about the universe crossing from one regime into another, and the asymmetry being generated in the crossing. The Affleck-Dine mechanism is not like that. It is a story about what happened after inflation ended, in the period when the universe was reheating, repopulating itself with particles, finding its way back to the thermal plasma from which Big Bang cosmology proceeds. And it begins not with a particle or a transition, but with a field sitting very still in a very strange landscape. In supersymmetric theories, and supersymmetry here requires a brief honest acknowledgement that it is a theoretical framework that has not been experimentally confirmed, that the particles it predicts have not been found at the LHC, and that its status is therefore that of a well-developed and mathematically consistent proposal rather than established physics. There exist, alongside the ordinary fields of the standard model, scalar partners for every fermion. Squarks, the scalar partners of quarks. Sleptons, the scalar partners of leptons. These fields carry baryon or lepton number in the same way their fermionic counterparts do. The potential energy landscape of these scalar fields has a property that is, in a specific technical sense, geographic. A flat direction is a path through field space, the abstract space of all possible field values, along which the potential energy does not change. Not a shallow slope, not a gentle gradient. Genuinely flat. So, place the field at any value along this direction, and it experiences no restoring force, no preference for one value over another. It is like a surface so precisely level that an object placed anywhere on it has no tendency to move, no preferred direction to roll, no pull toward any particular point. The flat direction in the Affleck-Dine mechanism is occupied by a condensate, a coherent macroscopic field configuration, where the scalar field has a large uniform value across a significant region of space. This condensate carries baryon or lepton number. It formed, in most versions of the mechanism, during or shortly after inflation, when the flat directions could be excited to large field values by effects related to the inflationary expansion itself. And then the universe changes around it. As the universe reheats after inflation and begins to cool, supersymmetry breaking, the process by which the perfect symmetry between bosons and fermions is lifted, introduces small corrections to the flat direction. The potential is no longer perfectly flat. Tiny tilts develop, and alongside these tilts, terms in the potential that violate CP symmetry, that distinguish between the condensate rotating one way in field space versus the other, begin to matter. Field space rotation is an abstract thing, but it has a physical analogy that is close enough to be useful. A gyroscope held in the hands has a rotation you cannot directly see, for the spinning is internal, but you feel it in the resistance when you try to change the gyroscope's orientation, in the subtle precession when you tilt it. The condensate in the Affleck-Dine mechanism rotates in field space in something like this way. The rotation is not spatial, but it is real. It has a direction, and the direction carries a charge. Rotating one way accumulates positive baryon number. Rotating the other way accumulates negative baryon number. The CP violating terms in the potential break the symmetry between these two directions, biasing the condensate to rotate preferentially toward one. The condensate rotates. The baryon number, or lepton number, depending on which flat direction is occupied, accumulates. The universe continues expanding and cooling, and the flat direction, which is only approximately flat, eventually develops a curvature as the energy scale falls. The condensate begins to oscillate, and at some point, determined by the specific form of the potential and the rate of the universe's expansion, the condensate decays. The decay is the hinge. When the scalar condensate decays into ordinary particles, the baryon or lepton number it has been carrying is transferred into the particle plasma. The net charge that accumulated through the CP violating rotation becomes a net excess of baryons over antibaryons or leptons over antileptons in the thermal bath. The sphalerons, if the decay happens above the electroweak scale, can then process a lepton asymmetry into a baryon asymmetry in the usual way. What results is the baryon asymmetry we observe, generated not at a phase transition, not through the decay of heavy neutrinos, but through the accumulation and transfer of charge stored in a condensate that spent the post-inflationary universe rotating slowly in an abstract landscape. The Affleck-Dine Mechanism is independent of leptogenesis and independent of Electroweak Baryogenesis. It does not require heavy right-handed neutrinos. It does not require a first-order phase transition. It requires supersymmetry and inflation, both of which are unconfirmed. But it requires them in ways that connect naturally to other motivations for those frameworks. The same inflation that solves the horizon problem, the same supersymmetry that addresses the hierarchy problem. Whether it is what the universe actually did, or one of several things it could have done, is genuinely open. The universe had more than one road to the same answer. The Affleck-Dine mechanism is a reminder that we have not yet established which road was taken, only that the destination was reached. Most of the time, when the cosmic microwave background appears in a conversation about cosmology, it arrives as a map. The oval projection, the pale mottling of slightly warmer and cooler regions, the colour scale running from red to blue, across temperature fluctuations of 1 part in 100,000. It is presented as the earliest image of the universe, snapshot of the cosmos at 380,000 years old, the moment when the plasma finally cooled enough to become transparent and light escaped for the first time. That framing is accurate. It is also incomplete. The CMB it is not only a map of early structure, it is a record of destruction. Every photon in that radiation field, every single one travelling for nearly 14 billion years before arriving at our instruments, was made from something that no longer exists. Not metaphorically made from, physically made from. Each photon carries the energy of particles that annihilated in the first second of the universe, matter and antimatter, meeting and converting entirely to radiation. The radiation then expanding and cooling across cosmological time until it reached a temperature of 2.725 degrees above absolute zero and filled the sky in every direction with a soothness broken only by those faint, informative ripples. Old paper absorbs the smell of wherever it has been kept. A document that has passed through many rooms carries something of each of them, not quite identifiable, just present, slightly altered, the record of its own history embedded in its texture. The CMB is something like that. It carries in its properties the record of everything that shaped it between the moment it was released and the moment it arrives, including what made it. The photon to baryon ratio, that number, approximately 6 baryons per 10 billion photons, is written into the CMB in a specific way. The plasma before a combination was not uniform. It was a fluid of photons, protons, electrons and dark matter, all coupled together in a medium where pressure and gravity competed. Sound waves propagated through this fluid, not sound in the ordinary sense, but compressions and rarefactions, pressure waves moving at roughly 60% of the speed of light, driven by the competition between radiation pressure pushing outward and gravity pulling inward. These waves oscillated for the 380,000 years before recombination, and when the plasma became transparent, they froze. Their pattern was imprinted onto the distribution of photons at decoupling, and that pattern is what we see in the temperature fluctuations of the CMB today. The acoustic peaks, the series of peaks and troughs in the CMB power spectrum, describing how much temperature variation exists at different angular scales, encode the physics of those frozen sound waves. The positions of the peaks depend on the geometry of the universe and the sound horizon at recombination. The heights of the peaks, particularly the ratio of the odd peaks to the even peaks, depend on the baryon density. More baryons means more gravitational pull relative to radiation pressure, which compresses the plasma more on the way in and produces a specific asymmetry between the compression peaks and the rarefaction troughs. Reading the peak heights gives you the baryon density, from the baryon density and the photon density, which is fixed by the CMB temperature. You get the baryon to photon ratio. The value, ETA approximately equal to 6.1 times 10 to the negative 10. Consistent with the value independently determined from Big Bang nucleosynthesis, which used entirely different physics, the reaction rates of protons and neutrons binding into light nuclei in the first 3 minutes, to arrive at its own measurement of the same ratio. 2 measurements, one from 380,000 years, one from 3 minutes, both pointing to the same number. The agreement is firm. Not surprising in the sense of being unexpected, the 2 measurements are consistent within the same cosmological model, and the model has been thoroughly tested. But firm in the sense that old paper is firm. It has held its shape across a long time and across many conditions, and what it says now is what it has always said. The ledger agrees with itself. What the ledger cannot tell you is why the number is what it is. Why 6 baryons per 10 billion photons rather than 60, or 6,000, or 0? The CMB encodes the ratio with precision. It does not encode the mechanism that set it. The acoustic peaks tell you how many baryons survived. They do not tell you what tilted the original asymmetry. There is a temptation, and I want to name it without giving into it, to call the photons of the CMB ghosts. Records of something that died. It is a word that arrives easily, and it is slightly wrong. Ghosts are presences that should not be here. These photons should be here. They are the expected physical consequence of annihilation, the energy that had to go somewhere, travelling forward through time as straightforwardly as any photon does. They are not haunting us. They are simply the evidence that something was lost, the evidence that something survived. Both truths in the same ancient light, arriving from every direction simultaneously, carrying a record that took nearly 14 billion years to deliver. The sky is made of what died. The ground beneath it is made of what didn't. Both facts are true. Both are written in the same light. If there were a place in the universe where a region of antimatter met a region of matter, where an antimatter galaxy drifted close enough to its matter surroundings for particles at the boundary to find each other, the interface would not be subtle. Protons and antiprotons meeting at the edge, electrons and positrons annihilating in the outermost gas, every collision producing gamma rays at a specific energy. 511 kiloelectron volts for electron-positron pairs. Higher energies for proton-antiproton annihilation. A glow at the boundary that no instrument sensitive to gamma rays could miss. We have instruments sensitive to gamma rays. We have been looking. Nothing like that boundary signal has been found, not in the nearby universe, not at galactic scales, not in the deep survey data that covers the observable cosmos out to billions of light years. The search has not been passive or casual. It has been conducted with dedicated space observatories, with careful analysis of diffuse backgrounds, with specific attention to the energy signatures that matter antimatter annihilation uniquely produces. The result, accumulated across decades of observation, is a null. A clean, informative, quantitatively significant null. Absence in ordinary experience feels like nothing, but in physics, absence can be a precise measurement, and this particular absence is one of the more constraining results in cosmology, even though it rarely receives attention proportional to its content. Not seeing something when you have looked carefully enough and long enough with sensitive enough instruments tells you that the thing is not there. The precision of the absence depends on the precision of the search. The European Space Agency's integral satellite, launched in 2002, has surveyed the sky in hard X-rays and soft gamma rays with particular sensitivity to the 511 kilo-electron-volt line, the characteristic energy of electron-positron annihilation. Integral has found that signal. It glows from the galactic center, a diffuse emission concentrated in the central bulge of the Milky Way, with a weaker disk component extending along the galactic plane. The signal is real and has been confirmed repeatedly, but it is not what a matter-antimatter boundary would look like. The galactic center 511 kilo-electron-volts emission is positrons meeting electrons in the interstellar medium of our own galaxy, produced by local astrophysical processes. The decay of radioactive isotopes synthesized in stellar interiors and dispersed by supernovae, possibly contributions from compact binary systems, possibly from cosmic ray interactions. It is antimatter, technically. But it is antimatter produced here, in a matter-dominated galaxy, by matter-based process. Its source is not a reservoir of primordial antimatter. It is ordinary high-energy astrophysics producing positrons in a universe made of matter. The signal that would indicate a genuine antimatter domain would look different, spatially extended, associated with a boundary rather than a central concentration, present at energies consistent with proton-antiproton annihilation products as well as the electron-positron line. None of those features have appeared in the integral data, nor in the gamma-ray surveys conducted by the Fermi Gamma-Ray Space Telescope, which has mapped the sky in the energy range from 20 megavolts to more than 300 gigavolts with a sensitivity that would register the boundary emission from an antimatter domain at cosmological distances if one existed within a range of several hundred megaparsecs. The sky, when you look at it in gamma rays, has a particular quality of flatness at the large scales relevant to this search. The eye, metaphorically, finds nothing to catch on. No bright seams, no luminous edges where two kinds of matter press against each other. Just diffuse emission from known astrophysical sources structured by the distribution of ordinary matter in the universe, carrying no signal of large-scale antimatter domains. The diffuse extragalactic gamma-ray background extends this constraint further. This background, the aggregate gamma-ray emission from all unresolved sources across the observable universe, has a spectrum that can be compared to predictions. If large antimatter domains existed at cosmological distances, their boundaries would contribute a specific component to this background, with a spectral shape and intensity calculable from the density of the intergalactic medium and the expected collision rates at matter-antimatter interfaces. The observed background is consistent with known source populations, blazars, star-forming galaxies, other astrophysical emitters, and shows no statistically significant excess attributable to annihilation boundaries. The constraints from this analysis place limits on antimatter domains that are quite precise. Domains smaller than a few megaparsecs, a megaparsec being roughly 3 million light-years, would have been detected if they existed within the observable universe in significant numbers. The matter-antimatter asymmetry, as far as these measurements can determine, is not a local feature. It is not the case that some regions of the universe went one way and others went the other way. With matter dominating here and antimatter dominating elsewhere, the asymmetry appears to be universal, established uniformly across the entire observable cosmos, with no large-scale antimatter reservoirs surviving anywhere within our observational reach. This is, in its quiet way, an important result. It means the baryogenesis mechanism, whatever it was, operated uniformly. It did not produce a patchy asymmetry, different regions, going different directions. It produced the same slight excess of matter over antimatter everywhere at the same time through a process that was either simultaneous across the observable universe or causal enough to establish the same outcome everywhere before the universe's regions fell out of causal contact, which places its own constraints on when and how the asymmetry was generated. The sky has no seams. That tells us something precise about the moment that made it. CERN calls it the Antimatter Factory, which is a name that carries more industrial suggestion than the reality warrants. The antiproton decelerator, the machine at the heart of the facility, takes antiprotons produced by firing a high-energy proton beam into a metal target, collects the antiprotons that emerge from the resulting particle spray, and slows them from near light speed to velocities manageable enough for experimental use. The process is technically demanding and the yields are very small. The CERN facility produces roughly 10 million antiprotons per minute during operation, which sounds like a large number until you calculate that at that rate, accumulating a single microgram of antimatter, a barely visible speck, would take more than 1 billion years. Factory is doing a lot of work in that name. But the quantities are not the point. The point is what you can learn from the antimatter you do manage to hold, and the holding itself is where the difficulty lives. Antiprotons and positrons, the anti-electrons, must be kept from contacting ordinary matter, which means keeping them suspended in a vacuum inside a magnetic trap. The field shaped carefully enough to confine charged particles without letting them drift into the walls of the apparatus. The trap is not containing something in the ordinary sense. It is containing something that would annihilate on contact with the container. There is a quality to that. Holding something in a magnetic field because you cannot hold it in your hands, that stays with you once you think about it. The Alpha collaboration at CERN began producing and trapping antihydrogen, a positron orbiting an antiproton, the simplest antiatom, in 2010. The numbers trapped in the early experiments were in the tens, later hundreds. Eventually, with improved techniques including laser cooling that reduced the antihydrogen temperature to around 1 millikelvin, large enough samples were available for precision spectroscopy. Spectroscopy of antihydrogen means measuring the frequencies of light that antihydrogen absorbs and emits. The same transitions that have been measured in ordinary hydrogen with extraordinary precision over decades. The most fundamental of these is the 1s to 2s transition, the excitation of the atom from its ground state to a specific excited state, driven by 2 photons of ultraviolet light. In ordinary hydrogen, this transition has been measured to 15 significant figures. It is one of the most precisely known quantities in physics. Alpha measured the same transition in antihydrogen. The result, improved over successive experimental runs, found the 1s to 2s transition frequency in antihydrogen to agree with the hydrogen to a precision of a few parts per trillion. Within measurement uncertainty, the frequencies are identical. CPT symmetry, or the combined symmetry of charge conjugation, parity, and time reversal, is one of the deepest symmetries in quantum field theory. It predicts that a particle and its antiparticle must have identical masses, identical lifetimes, and opposite charges. It predicts specifically that hydrogen and antihydrogen must be spectroscopic mirrors of each other. The same transition frequencies, the same energy level spacings, the same response to electromagnetic fields. The alpha spectroscopy results are a test of CPT symmetry at parts per trillion precision, and so far CPT holds. In 2023, alpha measured something different. Not a spectroscopic transition, but a gravitational response. The alpha G apparatus, a vertical version of the trap, designed to let antihydrogen atoms drift upward or downward when the magnetic confinement is released, measured the direction and approximate magnitude of gravity's effect on antihydrogen. The result, antihydrogen falls downward. Gravitational attraction, not repulsion. The weak equivalence principle, the rule that all objects fall the same way regardless of composition, appears to hold for antimatter as well as matter, at least to the roughly 20% precision of that first measurement. Anti-gravity, which had been a theoretical possibility some researchers had considered, appears not to exist. Then in 2026, Alpha measured the hyperfine splitting of antihydrogen, the tiny energy difference between two ground states caused by the interaction between the positron's spin and the antiproton's magnetic moment. The measurement was refined to a precision 100 times better than the previous best result. The hyperfine splitting of antihydrogen within experimental uncertainty matches that of hydrogen. Each result narrows the space in which matter and antimatter differ. Each measurement says with increasing precision, as far as we can determine, these two things are mirrors. Same mass, same spectral transitions, same gravitational response, same internal energy structure. And this is where the chapter reaches something that I find genuinely hard to sit with, not because it is paradoxical in a dramatic sense, but because it is quietly contradictory in a way that does not resolve. If matter and antimatter are this similar, if every precise measurement confirms the mirror, if CPT symmetry holds to parts per trillion in the most carefully studied antiatom we can produce, then where did the asymmetry come from? How did a universe whose fundamental laws treat matter and antimatter as reflections of each other manage to produce one and almost none of the other? The experiments at CERN are not finding a crack in the mirror. They are polishing the mirror to higher and higher reflectivity, and the better the reflection, the harder it becomes to explain why the universe looked into that mirror and produced almost entirely one side. The asymmetry is real. The matter is here. The mirror holds. All three of those things are true simultaneously, and they do not obviously fit together. The lab can measure the symmetry with extraordinary care. It cannot tell us why the universe broke it. The LHCb detector sits at one of the 4 interaction points along the Large Hadron Collider's ring, and it is built differently from the other large experiments there. Atlas and CMS are roughly cylindrical, surrounding the collision point in layers of detecting material designed to catch particles flying outward in all directions. LHCb is asymmetric, a single-arm spectrometer extending forward along the beam direction, optimized specifically for capturing the decay products of particles containing bottom quarks. The design choice reflects the experiment's purpose: to study, with very high precision, how particles built from bottom quarks behave differently from their antimatter counterparts. That difference, if it exists, where it exists, how large it is where CP violation lives in the quark sector. CP violation was first observed in 1964 in the decays of neutral kaons. It was later seen in B mesons, particles containing a bottom quark paired with an antiquark, confirmed independently by the Babar experiment in California and the Bell experiment in Japan in the early 2000s. Both of those discoveries involved mesons, particles built from one quark and one antiquark. The physics of CP violation in mesons is now well mapped. The CKM matrix describes it, the measurements confirm the description, and the standard model accounts for everything that has been seen in 2-quark systems. Baryons, particles built from 3 quarks, like the proton and neutron, are a different category. Heavier, more complex internally, with more decay channels and more opportunities for different types of the interference between decay amplitudes. Whether CP violation exists in baryon decays, and if so, how large it is and where it appears within the decay distributions, has been an open question. Not because there was theoretical reason to think baryons would be exempt. The CKM mechanism predicts CP violation in baryon decays as well, but because the measurements are harder and the signals smaller. In March 2025, LHCb published a result using the full dataset from their Run 1 and Run 2 operations, 9 inverse femtobarns of proton-proton collision data at center of mass energies of 7, 8, and 13 TeV. The particle under study was the lambda B baryon, 3 quarks, specifically an up quark, a down quark and a bottom quark, the same constituents as a proton, with one of the up quarks replaced by a bottom quark. That substitution is what makes the lambda B useful for this measurement, and also what makes it unstable. The bottom quark decays through the weak force, producing the final state particles that LHCb measures. The lambda B lives for roughly 1.5 trillionths of a second before decaying. The measurement looked at the decay lambda B to pk minus pi plus pi minus, the lambda B breaking apart into a proton, a kaon, and two pions. And it compared the rate of that decay to the corresponding decay of the anti-lambda B, the antimatter counterpart, into the same final state particles with opposite charges. If CP symmetry held perfectly, these two rates would be equal. If it is violated, they differ. The measured asymmetry, 2.45%. The lambda B decays into this particular final state 2.45% more often than the anti-lambda B decays into the corresponding antimatter final state after correcting for experimental effects. The uncertainty on that number, both statistical and systematic combined, puts the result at 5.2 standard deviations from zero. 5 sigma is the threshold. That is not an arbitrary convention. A result at 5 standard deviations means that if there were no real effect and the measurement were repeated many times, the probability of seeing a fluctuation this large purely by chance is roughly 1 in 3.5 million. At 5.2 sigma, the result sits comfortably past that threshold. It is an observation. CP violation has been seen in a baryon decay. The significance of crossing from mesons into baryons is real. It is not a bookkeeping achievement or a category check. Protons and neutrons, the particles that make up atomic nuclei that constitute the matter excess responsible for our existence, are baryons. If the matter-antimatter asymmetry of the universe ultimately traces to CP violation in the baryon sector, then understanding how and where baryons behave differently from antibaryons is directly relevant. The LHCb result demonstrates that this difference exists and is measurable with current technology, and it opens the 3-quark sector to systematic investigation in a way that was not possible before. The gap, though, remains enormous. The CP asymmetry observed is 2.45% in one specific decay channel of one specific baryon. The asymmetry required to explain the matter-antimatter imbalance of the universe, working backward through the Sakharov conditions, through the Sphaleron physics, through the thermal history of the plasma, requires CP violation at a level approximately 10 billion times larger than what the standard model's CKM mechanism can provide. The LHCb result is a measurement of CKM predicted CP violation, confirmed and extended into a new system. It is real CP violation. It is not enough. A door found is not the same as a door opened. The LHCb result tells us the door exists in this part of the building, that baryons carry CP violation, that the asymmetry is observable, that the measurement is now possible. It does not show what lies behind it. The explanation for our existence still requires a source of CP violation beyond anything the standard model contains, operating at conditions the LHCb cannot reach. What the result does is close one uncertainty. The 3-quark sector behaves as the theory predicted. The prediction was right, the measurement confirmed it, and the gap is exactly as large as it was before. That is both the value of the result and its limit. At 511 kilo-electron volts, the universe has a specific signature. When an electron and a positron meet and annihilate, 2 particles, 1 matter, 1 antimatter, converting entirely to radiation, they produce gamma rays at that energy. Not approximately. Exactly 511 kilo-electron volts, because that is the rest mass energy of each particle. And annihilation converts rest mass to photons with a precision that makes 511 kilo-electron volts one of the cleanest lines in the gamma ray spectrum. It is unmistakable. When an instrument sensitive to gamma rays sees that line, it is seeing the record of an annihilation event. Integral, the International Gamma Ray Astrophysics Laboratory, a European Space Agency satellite launched in 2002, sees that line glowing from the centre of the Milky Way, brightly, persistently. The emission is concentrated in the galactic bulge, the central region of the galaxy within a few thousand light-years of the core, and extends more faintly along the galactic disk. The Fermi Gamma Ray Space Telescope has confirmed the signal. The morphology is diffuse, not a point source, not a handful of discrete objects, but a broad, smooth glow centered on the galactic nucleus, like light from a source you cannot quite locate even though you can see its warmth spreading across the room. The brightness of the signal implies that something in the central regions of the Milky Way is producing positrons at a rate of approximately 2 times 10 to the 43 per second. That is a lot of positrons. Enough that whatever is making them must be either very numerous or very energetic or both. The signal has been known since the 1970s, detected first by balloon-borne instruments before satellites existed with this sensitivity to map it properly. It has been studied for decades. It remains unexplained. Not unexplained in the sense of having no candidates. There are candidates, several of them, each with genuine supporting arguments and genuine problems. Unexplained in the more uncomfortable sense that none of the candidates, individually or together, has been confirmed as the source, and some aspects of the signal's morphology resist easy accommodation by any of the proposed explanations. The most conventional candidate is low-mass X-ray binaries. These are systems in which a neutron star or black hole accretes material from a companion star, generating high-energy emission that can produce positrons through pair production and radioactive decay processes. They are present in the galactic bulge in significant numbers. Detailed population models of low-mass X-ray binaries can produce positrons at rates in the right order of magnitude for at least part of the observed signal. The problem is the spatial distribution, the signal's morphology, particularly its smooth and symmetric appearance centered tightly on the galactic nucleus, does not match well with the known distribution of these binary systems, which are more shuttered and less centrally concentrated than the emission profile suggests. Millisecond pulsars are another candidate. These are rapidly rotating neutron stars spun up by accretion, producing intense magnetic fields and high-energy particle winds capable of generating positrons. They are present in the central regions of the galaxy, and their positron output could contribute to the observed signal. The same morphological tension applies. The population of millisecond pulsars does not obviously trace the emission in the way a dominant source would need to. Radioactive isotopes offer a partial contribution. The decay of aluminum-26 as synthesized in massive stars and dispersed through the interstellar medium produces positrons at 511 kilo-electron volts when those positrons subsequently annihilate. This is a known and measured contribution to the galactic positron budget. It is not enough by itself to account for the full signal. And then there is dark matter. The central density of dark matter is expected to be high. The galactic center sits at the bottom of the dark matter potential well, and various models of dark matter distribution predict significant concentrations there. Certain dark matter candidates, particles with masses in the megavolt range, or scenarios involving dark matter annihilation or decay into standard model particles, could produce positrons at energies low enough to thermalize and annihilate at 511 kilo-electron volts. The spatial profile of such emission would, in some models, match the smooth and centrally concentrated morphology of the observed signal better than astrophysical source populations do. The problem is that the dark matter explanation is constrained from multiple directions. The mass and interaction cross-section required to produce the observed positron rate are in tension with limits from other observations, from cosmic microwave background measurements of dark matter annihilation in the early universe, from direct detection experiments, from other gamma-ray observations. It is possible, within some models, to accommodate the signal with dark matter contributions. It is not easy, and it is not confirmed. What the galactic center anomaly is, honestly, is a signal that has outlasted its simple explanations. The conventional sources each contribute something and none accounts for everything, and the combination has not yet been made to work in a fully satisfactory way. The dark matter explanation is constrained but not ruled out. The astrophysical explanations are plausible but morphologically uncomfortable. Something is producing positrons in the center of the galaxy. We are fairly certain about that. What that something is, whether it is one source or several, whether it connects to any physics beyond the standard model, or simply to astrophysical processes we have not yet fully characterized, remains genuinely open. The signal sits there, steady, unaccounted for. Not everything that glows has been explained. There is a map of baryogenesis theory that has accurate edges and a blank interior. The edges are well defined. The Sakharov conditions tell you what any solution must include. The Brion to photon ratio tells you what any solution must produce. The thermal history of the universe tells you when any solution must have operated. The edges of the problem are, in a technical sense, known. What sits inside them, the actual mechanism, the specific physical process, the particles and interactions responsible for the surplus that became everything, is not. This is not a gap from lack of effort. The problem has been worked on seriously for more than 50 years by a large fraction of the theoretical physics community, producing mechanisms that are each coherent, well-developed, and in their own ways insufficient. What the insufficiency of each tells us is not that physicists have failed. It is that the answer is stranger than the frameworks we have used to look for it. Start with the standard model's own contribution. The CP violation in the CKM matrix is real, measured, confirmed across multiple systems, but its magnitude when the calculation is run through the conditions of the early universe falls short of the observed baryon asymmetry by 19 orders of magnitude, not 19%, 19 powers of 10. The standard model can describe the shape of the solution. It has CP violation, it has Sphaleron processes, it has a cosmological expansion providing out-of-equilibrium conditions, but when asked to produce the number, it produces a number that is effectively zero compared to what is needed. The standard model is not an almost answer. It is, for this specific question, not an answer at all. Electroweak Baryogenesis was the candidate that came closest to being testable at currently accessible energies. It required new physics near the electroweak scale, additional sources of CP violation, modifications to the Higgs potential strong enough to make the electroweak phase transition first order, rather than the smooth crossover the standard model predicts. The LHC could, in principle, have found this new physics. It measured the Higgs boson mass at 125 giga-electron volts. It has run for 15 years at energies probing the electroweak scale in detail. The additional scalar fields, the enhancer P violation, the modified Higgs couplings that Electroweak Baryogenesis needs, none of them have appeared. The parameter space in which the mechanism works has not been fully closed, but it has narrowed considerably. What remains is a mechanism requiring physics that is increasingly hard to accommodate with what the LHC has actually seen. Leptogenesis does not have this problem exactly because it operates far above any energy scale the LHC can reach. The heavy right-handed neutrinos that generate the lepton asymmetry, if they exist, have masses anywhere from 1 billion to 10,000 trillion giga-electron volts. No collider built or currently planned approaches those energies. Leptogenesis is not ruled out by any measurement. It is also, for the same reason, not confirmed by any measurement. It is constrained indirectly by neutrino oscillation data, by the requirement that the Sphaleron conversion of the lepton asymmetry must complete before the electroweak phase transition, by the Davidson-Ibarra bound on the lightest right-handed neutrino mass. But the mechanism itself operates in a regime that may be permanently beyond experimental reach. Whether leptogenesis is the answer, or simply the most plausible story that cannot be checked, is a distinction that current physics cannot resolve. The Affleck-Dine mechanism carries its own requirement, supersymmetry, the flat directions that the condensate occupies, the scalar partners of quarks and leptons that carry baryon and lepton number, the specific form of the potential that allows the CP violating rotation to accumulate. All of these require the existence of superpartner particles. The LHC has searched extensively for superpartners at the TV scale. None have been found. Supersymmetry is not ruled out. The superpartners could be heavier than current search limits, or their decay signatures could differ from what the searchers assumed. But the most accessible and theoretically motivated region of supersymmetric parameter space has been explored and has come back empty. The Affleck-Dine mechanism requires a framework that is, at present, unconfirmed and increasingly pressured. Calling this an unsolved problem is accurate but slightly understating it. The problem is not that a solution exists and we have not found it yet, like a key that is somewhere in the house. It is that the solution may require particles, symmetries, or interactions that do not yet have names in any existing theoretical framework. Every mechanism currently on the table requires physics beyond the standard model, and none of those beyond standard model frameworks has been confirmed experimentally. The solution to baryogenesis is, at minimum, outside our most tested theory. It may be outside our most developed speculative theories as well. What the failures tell us is specific, though. The CP violation must be large, much larger than the CKM mechanism provides. The out-of-equilibrium conditions must be sharp, sharper than the standard model's electroweak crossover provides. The baryon or lepton number violation must operate at the right epoch, the right rate, through a process that leaves the correct residue. Each of these requirements, when the failed mechanisms are laid out honestly, becomes a constraint on whatever the correct answer turns out to be. The map has accurate edges, the interior is blank, but the edges are informative. They are not just a boundary, they are a description. Whatever fills the interior must fit inside them exactly. That is not nothing. It is, in a quiet way, progress. The shape of the unknown is known. Whether the correct mechanism is a variation of something already proposed, or something whose theoretical framework has not yet been written, is a question that remains open. The answer exists. The universe arrived at it. Once, in the first fraction of a second. What it used to get there is still, for now, its own. At some point in thinking about this, the physics stops being the hard part. The physics is difficult technically. The Sakharov conditions, the Sphaleron transitions, the CP violation in the CKM matrix, the heavy neutrino decay rates, all of it requiring careful thought and considerable mathematics to hold properly. But the difficulty of the physics is the ordinary difficulty of things that are complicated. Work through it long enough, carefully enough, and the structure becomes visible. The pieces have known shapes. Even the unsolved parts have defined edges. The hard part is something else. It is sitting with what the physics implies and not immediately reaching for a way to make it feel less strange than it is. 1 part in 10 billion. That is the margin. The difference between a universe that contains everything, stars, planets, chemistry, the accumulated weight of 13 billion years of structure, and a universe that contains nothing but light, expanding cold through an empty space, is 1 extra particle of matter per 10 billion matter, antimatter, pairs. Remove that margin and the annihilation completes. The ledger closes. The universe becomes radiation and nothing else, expanding and cooling forever through a space with no surfaces for the cooling to mean anything to. 1 part in 10 billion is not a large margin. It is in fact about as small a margin as you could specify while still being different from 0. And nobody knows why it is that number rather than 0. Nobody knows why it is that number rather than 2 parts in 10 billion, or 1 part in a trillion, or 1 part in a million. The physics that produced it, whatever mechanism, whatever process, whatever combination of CP violation and baryon number violation and out-of-equilibrium dynamics operated in the first fraction of a second, has not been identified. The number exists. Its origin does not yet have a confirmed explanation. There is a particular quality to a question that has no answer yet. Not frustrating exactly, just present. The way an unlocked door feels different from a locked one even when neither has been opened. There is something on the other side and you know that, and the knowing changes how the door feels without telling you what is behind it. This question has that quality. And then there is the stranger part. The part that is easy to state and difficult to fully absorb. The mind's asking the question, are made of the surplus, not made of matter in the generic sense, made specifically of the matter that survived the annihilation. Every proton in every atom in every cell of the person thinking about this right now is descended from that 1 in 10 billion excess. The neurons forming the thought, the question taking shape, the discomfort of not knowing the answer, all of it assembled from the residue. The asymmetry did not just produce matter. It produced the conditions for matter to organize over billions of years into structures capable of noticing that it existed and asking why. That is not a comfortable loop to sit inside. It is not uncomfortable either, exactly. I am not sure discomfort is quite the right response to it. It is more that the loop keeps closing in a way that seems like it should mean something and refuses to specify what. The question of why anything exists is, at its most precise, a question about a ratio. ETA approximately 6 times 10 to the negative 10. Why that number? What set it? What physical process, operating under what conditions, through what mechanism, produced a universe that kept one particle in 10 billion while discarding the rest? It is a physics question, a real one, with a real answer, somewhere in the first second of the universe's history. Not a philosophical placeholder, not a question that will dissolve on closer inspection into something unanswerable by definition. A physics question with a specific answer that the universe arrived at once, that left a specific, measurable trace that physicists are genuinely trying to find. If this is the kind of thing you want more of, if this video is worth your time, consider subscribing. And if you want to help the sleepy physicist keep going, the link to the Patreon is in the description. It makes more of this possible. The answer is not in hand. The frameworks that might contain it, Leptogenesis, Electroweak Baryogenesis, the Affleck-Dine Mechanism, extensions of the standard model not yet written, are each incomplete, each reaching towards something they do not quite touch. The correct answer may require physics that has not yet been theorized, particles that have not yet been named, symmetries that have not yet been noticed in the structure of the equations. That is not a comfortable place to leave things. But leaving things in a comfortable place when the comfortable place is not the accurate place is its own kind of problem. To the people who have supported this project, who have made it possible for these questions to be explored slowly, carefully, without rushing toward a false resolution, thank you. Genuinely. The ability to sit with an open question rather than closing it prematurely is something that takes both time and the people willing to give that time space to exist. The question is open. The surplus is real. We are it.